Physics plays a crucial role in sports, influencing everything from the trajectory of a basketball to the speed of a sprinter. One fascinating aspect is biomechanics, which studies the motion of athletes to optimize performance. For example, analyzing the angle at which a tennis player hits the ball can significantly impact the direction and speed of the shot. In fact, studies have shown that small adjustments in technique can lead to substantial improvements in outcomes. When it comes to forces, consider the incredible power generated by a baseball pitcher. The average fastball speed in Major League Baseball is around 93 miles per hour, with some pitchers reaching over 100 miles per hour. This impressive velocity is achieved through a combination of factors, including the pitcher's strength, technique, and the application of physics principles. Equipment design is another area where physics shines in sports. From aerodynamic cycling helmets to high-tech running shoes with energy-returning soles, advancements in technology have revolutionized athletic gear. In fact, the sports equipment market is estimated to reach $89.2 billion by 2025, reflecting the importance of innovation in enhancing athletic performance. As we delve deeper into the world of physics in sports, we uncover a realm where scientific principles intersect with human potential, pushing athletes to new heights of achievement. Biomechanics and motion analysis play a pivotal role in understanding and enhancing athletic performance. By studying the movements of athletes, researchers can uncover valuable insights that lead to improvements in technique, efficiency, and injury prevention. One fascinating aspect of biomechanics is the analysis of gait patterns in runners. Research has shown that optimizing stride length and frequency can significantly impact running economy and speed. For example, elite marathon runners typically have a cadence of around 180 steps per minute, allowing them to maintain a steady pace over long distances. In addition to running, biomechanics is also crucial in sports like golf, where the swing mechanics can make the difference between a successful shot and a missed opportunity. Motion analysis technology, such as high-speed cameras and motion capture systems, enables researchers to break down complex movements into precise data points. These tools provide valuable feedback to athletes and coaches, helping them fine-tune their techniques for optimal performance. When it comes to injury prevention, biomechanics plays a vital role in identifying movement patterns that may increase the risk of injury. By analyzing factors such as joint angles, muscle activation, and ground reaction forces, researchers can develop targeted interventions to reduce the likelihood of injuries. In fact, studies have shown that athletes who receive biomechanical feedback and training have lower injury rates compared to those who do not. The field of biomechanics is constantly evolving, with new technologies and methodologies being developed to enhance our understanding of human movement. For example, wearable sensors and pressure-sensitive insoles provide real-time data on biomechanical parameters during training and competition. These tools allow athletes and coaches to make immediate adjustments to improve performance and reduce the risk of overuse injuries. In the world of sports science, biomechanics serves as a bridge between physics and human movement, unlocking the secrets to athletic excellence and longevity. The impact of forces on athletic performance is a fascinating area of study that delves into the intricate relationship between physics and sports. When we think about forces in sports, one of the first things that comes to mind is the incredible power generated by athletes. Take, for example, a basketball player executing a slam dunk. The force exerted by the player on the ball as they propel themselves upward is a display of both strength and physics in action. In fact, studies have shown that the average force exerted by an NBA player during a dunk can range from 400 to 600 pounds, showcasing the immense physical capabilities of these athletes. Another intriguing aspect is the role of friction in sports performance. Friction, the force that resists motion when two surfaces come into contact, plays a crucial role in determining how athletes interact with their environment. For instance, in sports like ice hockey, the friction between the skate blade and the ice surface affects the player's ability to maneuver and accelerate. By understanding the principles of friction, athletes and equipment designers can optimize performance and enhance speed and agility on the ice. When it comes to impact forces, consider the sport of gymnastics, where athletes perform gravity-defying flips and twists. The landing impact forces experienced by gymnasts can be staggering, with studies showing that forces exceeding 14 times body weight can be absorbed during a landing. This highlights the importance of proper technique and training to minimize the risk of injuries. Overall, the impact of forces on athletic performance underscores the intricate interplay between physics, biomechanics, and human potential, shaping the way we understand and appreciate the physical feats achieved by athletes. Equipment design and technology have revolutionized the world of sports, pushing the boundaries of human performance to new heights. One fascinating example is the development of high-tech running shoes, such as the Nike Vaporfly, which have been shown to improve running economy by up to 4%. In fact, a study published in the journal Sports Medicine found that wearing these shoes could lead to a 3 to 4% improvement in running times, a significant advantage for competitive athletes. Another area where technology has made a significant impact is in the design of aerodynamic cycling helmets. These helmets are meticulously engineered to reduce drag and improve airflow, ultimately enhancing the speed and efficiency of cyclists. In a wind tunnel study conducted by researchers at the University of Southampton, it was found that wearing an aerodynamic helmet could lead to a reduction in aerodynamic drag by up to 10%, translating to faster cycling times. The sports equipment market is a booming industry, with global sales expected to reach $89.2 billion by 2025. This growth is driven by advancements in materials science, manufacturing techniques, and innovative designs that cater to the evolving needs of athletes. From carbon fiber tennis rackets to smart basketballs equipped with sensors, the marriage of design and technology continues to shape the future of sports equipment. As we witness the convergence of science and sports, we are reminded of the transformative power of innovation in enhancing athletic performance and pushing the boundaries of human potential. Fluid dynamics plays a crucial role in various sports, influencing everything from swimming to cycling. In swimming, drag is a significant factor that athletes must overcome to move efficiently through the water. By minimizing drag through streamlined body positions and advanced swimsuit designs, swimmers can achieve faster times. For example, the Speedo LZR Racer swimsuit, introduced in 2008, was designed using computational fluid dynamics to reduce drag and enhance buoyancy, leading to numerous world records being broken. In cycling, aerodynamics are paramount, with cyclists striving to reduce air resistance to maximize speed. The Tour de France, one of the most prestigious cycling races, showcases the importance of aerodynamics in a sport where every second counts. Studies have shown that up to 90% of a cyclist's energy is used to overcome air resistance, highlighting the critical role of fluid dynamics in cycling performance. Another fascinating application of fluid dynamics is seen in the sport of sailing. Sailboats harness the power of wind to propel them forward, with the shape and design of sails playing a crucial role in capturing and utilizing the wind's energy. The America's Cup, the oldest international sporting trophy, features cutting-edge sail designs that push the boundaries of fluid dynamics to gain a competitive edge. In fact, the latest America's Cup boats are equipped with foils that lift the hull out of the water, reducing drag and increasing speed. The intersection of fluid dynamics and sports continues to drive innovation and push the limits of human performance, showcasing the profound impact of science on athletic achievement. Energy and power are fundamental components of athletic performance, influencing the speed, strength, and endurance of athletes across various sports. In track and field, sprinters rely on explosive power to propel themselves down the track at astonishing speeds. Usain Bolt, the fastest man in the world, recorded a top speed of 27.8 miles per hour during his world record 100-meter sprint in 2009. This incredible display of power and speed showcases the immense energy output required for elite sprinting. In contrast, endurance athletes like marathon runners rely on sustained energy production to cover long distances. The average male marathon runner burns around 2,500 to 3,000 calories during a race, highlighting the significant energy demands of endurance events. Power is another critical factor in athletic performance, particularly in sports like weightlifting and shot put. Weightlifters generate explosive power to lift heavy loads overhead, with the world record for the clean and jerk standing at 583 pounds for men and 417 pounds for women. Similarly, shot putters rely on power to launch a heavy metal ball as far as possible. The current men's world record in shot put stands at 73 feet and 8¼ inches, achieved by Randy Barnes in 1990. These impressive feats of power demonstrate the incredible strength and explosiveness required in power-based sports. The concept of power-to-weight ratio is also crucial in sports like cycling and climbing, where athletes must generate power relative to their body weight. In cycling, the power output of elite riders can exceed 600 watts during intense efforts, allowing them to conquer steep climbs and sprint to the finish line. Rock climbers, on the other hand, rely on power-to-weight ratio to navigate challenging routes, with the ability to generate force while maintaining a low body weight being a key determinant of success. Understanding the interplay between energy production and power generation is essential for athletes looking to optimize their performance and achieve their full potential. Friction and surface interaction play a critical role in sports, influencing the performance and outcomes of athletes in various disciplines. In sports like tennis, the type of court surface can significantly impact gameplay. For example, clay courts provide more friction, allowing players to slide and change direction quickly, while grass courts offer less friction, resulting in faster ball speed. In fact, studies have shown that the coefficient of friction between a tennis ball and different court surfaces can vary by up to 20%, highlighting the importance of surface interaction in the game. Another sport where friction plays a key role is ice hockey. The friction between the skate blade and the ice surface determines the player's ability to maneuver, accelerate, and stop effectively. NHL players can reach speeds of up to 25 miles per hour on the ice, relying on precise control of friction to navigate the rink with agility and speed. In gymnastics, the interaction between the athlete's hands and the apparatus is crucial for executing complex maneuvers. The balance beam, for example, requires a delicate balance of friction and grip to perform leaps, turns, and acrobatic elements with precision. Gymnasts train rigorously to master the nuances of surface interaction, ensuring a seamless connection between their movements and the equipment. Understanding the role of friction and surface interaction in sports is essential for athletes and coaches seeking to optimize performance and technique. By harnessing the principles of physics and biomechanics, athletes can leverage friction to their advantage, whether it's maximizing grip on a climbing wall or controlling speed on a ski slope. The intricate dance between athletes and their environment, shaped by friction and surface properties, underscores the dynamic interplay between science and sport. Injury prevention is a critical aspect of sports performance, and physics plays a key role in understanding and mitigating the risk of injuries. One fascinating application of physics in injury prevention is the analysis of impact forces on the human body during athletic activities. For example, studies have shown that the force of impact experienced by a soccer player heading the ball can be equivalent to a collision at 25 miles per hour. By understanding the physics of impact forces, researchers can develop strategies to reduce the risk of head injuries in soccer and other contact sports. Another intriguing area of injury prevention is the use of biomechanical modeling to assess the risk of overuse injuries in athletes. By analyzing factors such as joint angles, muscle activation patterns, and ground reaction forces, researchers can identify movement patterns that may predispose athletes to injuries. In fact, a study published in the Journal of Sports Sciences found that runners with higher impact forces during running were more likely to experience injuries such as stress fractures. By incorporating biomechanical principles into training programs, coaches and athletes can optimize movement patterns to reduce the risk of overuse injuries. The field of sports equipment design also plays a crucial role in injury prevention. Advances in materials science and technology have led to the development of protective gear that can mitigate the impact of collisions and falls. For example, helmets equipped with impact-absorbing materials can reduce the risk of head injuries in sports like football and cycling. In the world of sports science, the application of physics principles to injury prevention is a dynamic and evolving field that holds great promise for enhancing athlete safety and performance. Training optimization with scientific principles is a cornerstone of athletic success, where the application of data-driven approaches can lead to significant performance gains. One interesting aspect is the use of heart rate variability, HRV monitoring, to tailor training programs to individual athletes. HRV analysis provides insights into an athlete's readiness for training, allowing coaches to adjust the intensity and volume of workouts based on real-time physiological data. Studies have shown that athletes who follow HRV-guided training programs experience improvements in performance and recovery. In fact, a study published in the Journal of Strength and Conditioning Research found that HRV-guided training led to a 12% increase in peak power output compared to traditional training methods. Another fascinating technique is the use of velocity-based training, VBT, to optimize strength and power development. VBT involves measuring the velocity of a barbell during resistance training exercises to determine the athlete's level of effort and fatigue. By adjusting training loads based on barbell velocity, coaches can ensure that athletes are training at the appropriate intensity to maximize gains in strength and power. Research has shown that incorporating VBT into training programs can lead to greater improvements in strength and power compared to traditional percentage-based training. For example, a study published in the Journal of Sports Sciences reported that athletes who used VBT saw a 20% increase in squat strength over a 12-week training period. The integration of scientific principles into training optimization represents a paradigm shift in sports performance, where data-driven approaches are reshaping the way athletes train and compete. In the realm where physics and sports intersect, a world of fascinating details and intriguing facts unfolds. Did you know that the average force exerted by an NBA player during a dunk can range from 400 to 600 pounds? This incredible display of power showcases the immense physical capabilities of these athletes. When it comes to cycling, up to 90% of a cyclist's energy is used to overcome air resistance, emphasizing the critical role of aerodynamics in maximizing speed. In gymnastics, the balance beam requires a delicate balance of friction and grip to execute complex maneuvers with precision. The America's Cup, the oldest international sporting trophy, features cutting-edge sail designs that push the boundaries of fluid dynamics to gain a competitive edge. The Tour de France showcases the importance of aerodynamics in cycling, with cyclists striving to reduce air resistance to maximize speed. In the world of sports equipment design, the market is expected to reach $89.2 billion by 2025, driven by advancements in materials science and innovative designs. The Speedo LZR Racer swimsuit, designed using computational fluid dynamics, has been shown to improve running economy by up to 4%, leading to numerous world records being broken. In the field of injury prevention, the analysis of impact forces on the human body during athletic activities has led to strategies to reduce the risk of head injuries in sports like soccer. By incorporating biomechanical principles into training programs, coaches and athletes can optimize movement patterns to reduce the risk of overuse injuries. The integration of scientific principles into training optimization represents a paradigm shift in sports performance, where data-driven approaches are reshaping the way athletes train and compete. From heart rate variability monitoring to velocity-based training, athletes are leveraging cutting-edge techniques to maximize gains in strength, power, and performance.